All right, let's go ahead with this. So welcome to the next seminar in the Exoplanet Seminar Series here at Goddard. Our speaker today is Anjali Piette. She is a final year PhD student working with Niku Madhusudan at Cambridge, working on exoplanet atmospheres. I'm going to make this really short introduction. So we have plenty of time for questions later. Her talk is on radiative processes of substellar atmospheres across the mass range. Take it away, Anjali.
Thank you for the introduction. So yeah, thanks for having me here. As Preval said, I'll be talking about exoplanet atmospheres really across the range from brown dwarfs all the way to mini-Neptunes. And the great thing about, I'm sure I don't need to convince you, the great thing about learning about these atmospheres is that through observing them, we learn not only about the thermal properties and the chemistry of the atmosphere itself, which is hugely interesting and tells us a lot about the atmosphere, but it also gives us clues about other parts of the planet. For example, links with the deeper physics inside the planet. The chemistry can give us links to the formation. This kind of observation can also tell us about energy transport in the atmosphere. So there's so much physics to be learnt about from the atmosphere. And as I'm sure I don't need to explain, there are many different ways to observe atmospheres, including through transmission spectra, secondary eclipse measuring the thermal emission, and also direct imaging. But just to be clear from the start, what I'll be talking about today is focusing on thermal emission, both direct imaging of isolated brown dwarfs and also secondary eclipse of mini-Neptunes that are transiting. So one of the reasons I love thermal emission spectra is that it doesn't just tell you about the chemistry of the atmosphere, which is super useful. And like in this plot, for example, I know it looks a little bit complicated, but basically these purple squiggles are showing which parts of the atmosphere are sensitive to different species. And they're showing us that the spectrum is actually really sensitive to those different abundances. So it's a great way to learn about the chemistry. But the other great thing is that we can learn a lot about the temperature profile in the atmosphere. So here on the top left is just an example of how different slopes in the atmospheric temperature profile can lead to very different spectra, thermal emission spectra. And that means that these observations can really allow us to constrain the temperature profiles in these planets and brown dwarfs. The flip side of that is that when we're interpreting thermal emission spectra, it's really important to understand these temperature profiles, both in terms of if you're doing an atmospheric retrieval, it's very important to parameterize your temperature profile or model it in a way that means you can properly interpret that spectrum. And in general, it is very important to understand the different processes and to know what we're expecting, because it can have a huge impact on what you infer from the thermal emission. So there are many different ways to understand those PT profiles. I briefly mentioned already atmospheric retrievals, where we're driven by the data and we see what kind of temperature profile we get from that. And also you can use self-consistent atmospheric models. Obviously there are many different types, many different dimensions, but in this talk I'll be talking specifically about one-dimensional self-consistent atmospheric models. And both of these tools can really help us to learn about the temperature profiles in many different kinds of exoplanet atmospheres. And in this talk, I'm going to talk about two opposites in this space of the methods versus mass. I'll start off by talking about atmospheric retrievals of brown dwarfs, isolated brown dwarfs. And then in the second half, I'll talk about self-consistent atmospheric models of transiting mini-Neptunes. So let's start off with the brown dwarfs. So one of the reasons that we were motivated to work on this is that there's amazing data available for isolated brown dwarfs. For example, with Hubble data, this just shows you the difference in the signal to noise that we can get between a hot Jupiter and an isolated T-Dwarf. This is a signal to noise of about 1,000, which is a huge improvement. So it's not only a great way to learn about these brown dwarfs in their own right, but also it's hopefully a glimpse of what we might be able to achieve one day for exoplanets. And so learning about how to interpret these observations and the considerations that we need to think about is in a way to prepare for these better exoplanet observations of the future. So the reason that we can get such high signal to noise data for brown dwarfs is partly because if they're isolated, there's no stellar contamination that needs to be removed. Also, these are higher gravity objects, so they have nice broad features, but crucially, the temperature gradient in these isolated brown dwarfs is very steep. And that means that you have very, very strong absorption features. that are very easy to make out in the spectrum. And before jumping into these retrievals, obviously a lot of work has been done on brown dwarfs, including classifying them analogously to stellar classifications. And in particular, two of those classifications are the L-dwarfs and T-dwarfs, which are classified based on their observed spectra. So we already know from all this work some of the chemical species which we're expecting to play an important role in shaping those thermal emission spectra. And for example, for T-dwarfs, species like water and methane are very, very important in the near infrared, including hydrogen-hydrogen and hydrogen-helium collision-induced absorption, ammonia, and sometimes even CO is seen in disequilibrium. Another difference between L-dwarfs and T-dwarfs is clouds. So L-dwarfs are observed to be pretty variable, and that's thought to be due to patchy cloud cover, whereas T-dwarfs on the whole tend to be less variable, and it's thought the clouds actually sink to below the photosphere. And so in this example, we're exploring these retrievals, and to keep things simple, we chose to focus on cloud-free T-dwarfs and to leave the clouds for another day. So the general retrieval framework that I'll be talking about looks a little bit like this. We have a parametric model, first of all, which we use to fit the data using a Bayesian inference algorithm. And in particular, we're using nested sampling. And this is actually a framework that was developed by Sid Gandhi in 2018 with my supervisor Madhu. And it was originally developed for hot Jupiters. And so in this work, what we did was to adapt that and to think about what needs to change to retrieve these really high signal to noise spectra of isolated T-dwarfs. And so let's have a look in more detail at this parametric model. So one big difference between hot Jupiters and these isolated brown dwarfs is that we don't necessarily know their gravity, their radius, or the distance to the object. So they're all parameters that we have to include in the retrieval as well. And since the radius and the distance are perfectly degenerate, we include those two as a single radius distance ratio in the retrieval. As I've alluded to before, the way that we parameterize the temperature profile is also really important. So I'll be going into more detail in the next couple of slides on that. But that's another set of parameters that we include are the parameters for the temperature profile. And then we also have the chemical abundances as parameters, and we're using chemical cross sections from the latest databases, including ExoMol, HiTemp, and HiTran. And when we put all of those ingredients together, we get out a model spectrum, which we can compare to the data. So coming back to this temperature profile parameterization, just zooming out for a moment, the reason that we need to do something a little bit different to the hot Jupiters is for two main reasons. The first one is that, as I mentioned before, the temperature gradient in these objects is very, very steep, and the spectrum is very, very sensitive to that temperature gradient. So as you can see here, even if we change the slope deep in the temperature profile just a little bit, it can change the spectrum significantly. And when we consider the tiny error bars in the data, this is going to be a really important factor. So whatever parameterization we're going to use, it has to have the flexibility to fit that slope accurately. And another thing to consider is that because these objects have a slightly higher gravity than our typical hot Jupiters, the photosphere is actually a bit deeper and can go up to a few tens of bar in some cases. So the temperature profile needs to be very flexible, and it needs to stay flexible even to those higher pressures. And there are different ways to go about doing this, but we came up with this parameterization, which consists of several layers in the atmosphere. And just to give you a sense of how to think about this in a way, how we thought about it, one way to give full flexibility to the temperature profile is to say, okay, for each pressure level, we'll define these temperature points, and we'll let those temperature points do whatever they want. We give the temperature profile full freedom. The problem with that is that with these observations and with thermal emission spectra in general, the temperature profile is a great way to overfit the data. So what you end up with are these horrible oscillations, which are just numerical artifacts, and we want to avoid that. So since in these isolated objects, we're not expecting any thermal inversions, so we're expecting the temperature to only increase as we go deeper into the object, that means that one way we can try to omit these oscillations is to not allow any thermal inversions at all, such that these oscillations are excluded. One way to do that is to pose conditions on the temperature profile within the retrieval and to say, okay, if it has a thermal inversion, I reject that sample and I give it a very low likelihood. But that means rejecting a lot of samples, and it's not actually a practical way forwards. So what we did was to define these parameters, delta T parameters, that are actually the change in temperature across each pressure level. And that way we can actually set the priors on those delta T parameters such that the temperature can only increase as you go down. And by doing that, we're able to restrict the prior space of temperature parameters to temperature profiles that don't have these thermal inversions and don't have these huge oscillations, which makes it, it's still very flexible, but we're removing all this unphysical space that we don't want. And then finally, of course, you need an anchoring temperature, and we put that at around 3 bar because that's roughly in the middle of where we expect the photosphere to be. So we should be able to constrain the temperature there. So that's the new parameterization for the temperature profile that we're using. Another big consideration that we thought about is model uncertainty. And the reason for that is that the error in the model we found could actually be greater than the uncertainties on the data. And so it's another way to overfit the data basically with the uncertainty in the model, which isn't what we want either. So we first of all wanted to quantify to a certain extent the minimum amount of model uncertainty that we thought there might be. Obviously, that'll always be a minimum. There's always more uncertainty in the model. And then the next step was then to include knowledge of this model uncertainty into the retrieval. So I'll start off with this quantification. The 2 main sources of model uncertainty that we considered were those due to vertical resolution. So that's how many pressure layers do we use in the atmosphere to calculate radiative transfer. So this is separate to the parameterization that I just mentioned, and it's really for the calculation of radiative transfer. And for that, we found that, of course, the more levels you have, more layers and higher resolution you have, the better the accuracy of the model. But it's a compromise between accuracy and computation time. So we decided in the end to go with 100 pressure levels in the atmosphere, and that gives us a good compromise there. So the second source of model uncertainty we looked at was the spectral resolution. We're calculating these models line by line. So obviously the resolution that we're calculating the model spectrum at isn't at the same very high resolution of the cross sections. So one way to sample the cross sections is by point sampling. So we just take samples at regular intervals. But alternatively, we could also, for each of those sampled bins, we could work out the log median or the geometric mean or the arithmetic mean in that bin. And we wanted to compare those different methods and also compare different spectral resolutions for each of those methods. And we found that in general, the point sampling and log median methods gave us the best accuracy. And in particular, once we got to a larger number of bins, like 4,000 bins in the JWST3 spectral range, so 1.1 to 1.7 microns, we found that the log median performed a little bit better. So that's what we've chosen to go for, 4,000 spectral bins with this log median method. And all in all, with these different considerations, this gives us a minimum model uncertainty of about 8%. And so that's something that we want to propagate forwards into our assessment of the spectrum. And the way we do that is by, first of all, we know that we don't know the full, there are many unknown sources of uncertainty that we want to include. So we add a parameter into the retrieval, and this goes into the log likelihood calculation when we compare each model to the data. And what we do is, instead of just using the data uncertainty, we inflate that by an added unknown uncertainty, which we parameterize with this xTOL parameter. And we know that xTOL has to be at least 8% because we know we have at least 8% uncertainty in the retrieval, and it could be higher than that. So our way of including the model uncertainty is by setting a prior on the xTOL parameter, a lower bound prior 8%, and allowing it to extend to higher values. And that's what's done here for the blue posteriors in this test retrieval. But for the purple posteriors, the very narrow ones, we allowed xTOL to go right down to 0 so that the retrieval could choose to have no model uncertainty if it wanted. And we can see that, well, first of all, if it has the chance to see no model uncertainty, it does that, and it has very, very narrow posteriors. And And on top of that, it might not be super clear because these narrow posterior distributions are very close to the true values, which are shown by the yellow dashed lines. But actually, most of these are much more than 1 sigma away from the true values. Whereas with the blue posteriors, where we include this model uncertainty, all of the retrieved values are within 1 sigma, which is what we'd like to see. And so, yeah, including this model uncertainty is actually important in this case. So those are the main new model considerations that we've put into this retrieval. And the next step is to test this on a simulated data set. So what we did was to simulate a spectrum at the highest possible resolution. So as I mentioned before, we tested these higher spectral and vertical resolutions. That's too computationally expensive to do for every model in the retrieval, but we used those just to calculate one very high resolution model to simulate our data. And we based this on a benchmark test case from Lionel 2015 of Gliese 570D. And the temperature profile that we use for this simulated data is this self-consistent PT profile that's shown in this paper. And we can see that the retrieved temperature profile, which is these the dark brown line and with 1 and 2 sigma contours in orange, we are accurately retrieving the temperature, especially in the photosphere, and also at the lower pressures and the higher pressures where the spectrum isn't really sensitive to those pressures. The temperature profile is telling us that it doesn't know as much by showing these larger uncertainties in those regions. And the spectrum is also very well fit by the model. And these are the posterior probability distributions that we get for some of the model parameters. In particular, for the chemical abundances, we retrieve those to within about 0.1 dex. So 1 sigma uncertainties are about 0.1 dex, which is really great for, a great precision for these chemical abundances and is really on the upper limit of what's possible with Spectra today. So that's great, that's looking very promising. Another thing that's interesting to look at with these simulated data sets is the different correlations that you can see between the parameters in the retrieval and the different degeneracies. And in particular, I'd like to talk about this one between the log gravity and the chemical abundances of the principal chemical species affecting the spectrum. So in this case, that's water and methane. And you can see this very strong correlation between these parameters. And the reason is that both the gravity and the chemical abundances are affecting the optical depth of the atmosphere. And therefore, they are very degenerate. It's not a perfect degeneracy because there are these 2 different species affecting the spectrum, but it is a very strong degeneracy. And so this is something that in future, to improve our constraints, we might want to look into ways of breaking this degeneracy, for example, by looking at a wider spectral range and trying to get features from other species as well. So now I'll move on to a retrieval we did for a real data set. So this is data for 2 mass 2339+13, which is a T4.5 dwarf from Brensley et al. 2014, and we chose this brown dwarf because it shows very, very little variability. So ideally, not so much effect of clouds in the spectrum. And this is the temperature profile we retrieve, and the photospheric temperatures from this temperature profile correspond well with the effective temperatures that we would expect from this kind of object, which is great. And we're also managing to fit the spectrum very well. This slightly messier part of the spectrum is happening due to some potassium features. I won't go into like all the detail, but we found that actually the potassium isn't affecting our other retrieved parameters at all. So it can change, whether you include potassium or not, can change the fit to the spectrum, but it doesn't affect the rest of the analysis. So these are the posterior distributions that we get for the different parameters. And again, for the chemical species, we're getting 1 sigma uncertainties of about 0.1 dex, which is great. So the same as we got for the simulated retrieval. And in general, we're getting fairly subsolar abundances. I'll note that we also get slightly low gravities. And so one thing to think about is, this is why I mentioned the gravity and abundance degeneracy. One question is whether that is playing into this result or whether this is real. So I think in the future, exploring that degeneracy and how to break it will be important in understanding these retrievals. So just as an intermediate summary, this brown dwarf data is really great. It's a glimpse towards the future of exoplanet observations and a great way to learn more about brown dwarfs. And the two main new considerations that we've thought about here are considering model uncertainty and considering a new temperature parameterization for these objects. And we're getting great precision for the chemical abundances. So that's the first half over. And now I'm going to move on to mini-Neptunes and looking at their atmospheres with self-consistent models. So the reason, well, there are many reasons why we want to study mini-Neptunes. For one, they're one of the most common types of planets detected to date. And it's at that really exciting time right now where we're being able to start to characterize their atmospheres, and we're getting chemical constraints for several mini-Neptunes. And at the same time, they're very mysterious objects. We don't have one in the solar system, and there are many degenerate solutions for the interior structure and different possibilities for the origins of their atmospheres. So I think they're really exciting objects to be studying right now. And so what we wanted to do in this work was to explore different atmospheric conditions in mini-Neptunes. And we're doing that using a self-consistent atmospheric model. This is based on the Genesis model developed by Sid Gandhi and Madhu in 2017. And this model solves radiative convective equilibrium, hydrostatic equilibrium, and thermochemical equilibrium. And we've also added some cloud and haze prescriptions for this work as well. I won't spend too long on the messy equations, but I just wanted to put this up just in case anyone's interested. And the main message is that the methods we're using to solve radiative transfer and radiative convective equilibrium are the algorithms used for stellar models. So we're using the Rybicki method to solve the equations of radiative convective equilibrium, and the Filtrier method and the discrete finite element method for the radiative transfer. And these are direct solutions to the equations, and we solve them to the second order. So they're robust calculations. So now getting on to the results of those models, we wanted to explore, first of all, a bunch of different atmospheric conditions, including different internal temperatures, different heat fluxes coming from the center of the planet, different irradiation conditions, different infrared opacities, which we're scaling as the metallicity, and both for clear atmospheres and also atmospheres with haze. And here we are parameterizing the haze as enhanced Rayleigh scattering from hydrogen. So I'll start off with the clear models. As we can see, the internal temperature has a significant effect on the temperatures deeper in the atmosphere. But these sort of darker gray bars, these are showing the photospheres for each model. And we can see that in this case, although the internal temperature is having a significant effect at higher pressures, it's not really affecting the photosphere. So it's going to be difficult to assess directly from the thermal emission from the day side. On the other hand, as you'd expect, the irradiation changes the temperature of the whole atmosphere exactly as we'd expect, and that does have a huge effect on the photosphere. And for the infrared opacity, as you would expect, as you increase the metallicity, you make the atmosphere hotter, but the photosphere also moves to lower pressures. And this is something that was also noticed by Spiegel et al. 2010, and that's that the temperature of the photosphere actually doesn't change a huge amount as you change the metallicity of the atmosphere. So that's quite an interesting effect. When we consider haze now, the bottom row in these plots, we see similar trends, but the haze is effectively undoing some of the greenhouse effect from the rest of the atmosphere. And so one thing we notice is that the internal temperature has an even stronger effect on the temperature of the lower atmosphere, a very noticeable effect. And also the radiative convective boundary. So I should say these thicker segments are convective regions in the atmosphere. And so if you have a hazy atmosphere and a high internal temperature, the radiative convective boundary can really climb to lower pressures. And actually on a similar note for the infrared opacity, as we would expect, the higher opacities give us some convective zones in different parts of the atmosphere because it's prohibiting radiative transport. So these are the effects on the temperature profile. So I also want to show you the effect on the thermal emission spectra. So as expected, the internal temperature doesn't have a huge effect on the spectrum. So these plots are laid out in the same way as the previous one. And so, yeah, different internal temperatures, unless it's a very, very high internal temperature, for example, 200 Kelvin, we don't see much difference between the thermal emission spectra. The irradiation, as expected, does have a huge effect, and that's something that we can see. We can see that difference in the photospheric temperature. And with the infrared opacity, as I mentioned, the temperature of the photosphere doesn't differ very much between these different models. So although the shapes of the features will be different, the overall level of that thermal emission is actually quite similar between the different cases. So moving on now onto another family of atmospheric parameters, and these are the haze and cloud parameters. So as I mentioned, we're modeling haze here as an enhanced Rayleigh scattering, and we're also including different kinds of clouds. In this case, the clouds aren't self-consistent with the temperature profiles. What I've done is to include a cloud at a fixed pressure. So here it's a deep cloud at 10 bar, and it's a salt cloud, whereas here it's a cloud at 0.1 bar due to ice. And I'm changing the opacity of those clouds, changing the metallicity and cloud particle abundances to see how that affects the temperature profile. So with the haze, we can see that, of course, it's undoing that optical scattering is undoing the greenhouse effect and really strongly cooling the atmosphere and making the temperature profile much more isothermal. With the deeper cloud, the effects are really happening deeper in the atmosphere. So unlike the haze, where there's an effect on the photosphere in some cases, the photosphere here isn't greatly affected, but the temperature deep down in the atmosphere is affected still. And for the shallower clouds, because those clouds are very close or even inside the photosphere, they're making a difference to the temperature of the photosphere and also changing the temperature conditions deeper down in the atmosphere. And these are the spectra, the thermal emission spectra corresponding to those different cases. As expected, the deeper cloud doesn't make much difference, but for the different haze opacities and the shallower clouds, those different abundances really do make a difference that is somewhat noticeable in the thermal emission spectrum. And I should note that here we're really looking at the longer wavelengths because these are very cool objects. The case I'm showing in particular is around 300 Kelvin. So yeah, we really need to look more into the mid-infrared to see this signal. So those are some of the more general ways that all these different atmospheric conditions can affect the temperature in the atmosphere and the thermal emission spectrum. But another thing I'm really interested in is how that links to what might be below the atmosphere. So for example, many models for mini-Neptunes and ice giants will include a significant layer of volatiles, for example, a water layer beneath a hydrogen-helium atmosphere. And so if we know the temperature profile in the atmosphere, we know that whatever temperature and pressure conditions are at the base, they are the temperature and pressure conditions at the surface of this potential water layer. And it can actually tell us what phase we would expect at this surface. So what we wanted to do was to look at how these different atmospheric conditions could affect a potential surface with a water layer deeper down. So this is just a quick diagram to explain the plots that are coming up. The phase diagram in the background is the phase diagram for 100% water. So that corresponds to the 100% water layer that we're imagining is beneath the atmosphere. And this temperature profile is calculated to high pressures, but because the surface pressures we're considering are deeper than the photosphere, instead of calculating a separate temperature profile for each surface pressure, that's actually not necessary because it'll be the same. So here what we can do is we see this temperature profile and we can say, if a surface with a water layer exists at, for example, close to 1000 bar, then these are the pressure temperature conditions that we would expect at that surface. And that would mean that the water layer beneath the atmosphere would be in a supercritical state if there's a clean distinction between the atmosphere and the water layer. On the other hand, if the surface occurs at a couple of hundred bar, then that water layer will be in the liquid phase at that boundary. And if we cut it, say, at 10 bar, the surface will actually still be liquid, but it'll be at cool enough temperatures that it's sort of quote unquote habitable. Here I'm defining habitable as pressures and temperatures that are below the pressures and temperatures known to be habitable on Earth by extremophiles. So that's around 1,000 bar and around 400 Kelvin, because there are extremophiles on Earth that can survive those conditions. Of course, there may be other kinds of life that can survive something more extreme, but this is just a starting point. So just to avoid confusion, I just want to emphasize that the phase of the atmospheric H2O, the vapor, well, it is all in vapor phase, and that's because the partial pressure of water in the atmosphere is lower than in the 100% water layer. So actually the phase of that is all in the vapor, which sometimes that can be misleading with this phase diagram. So to do this investigation, we wanted to choose the case study of K218b. So as you may know already, this is a habitable zone mini-Neptune with an irradiation temperature that's around 300 Kelvin. And with its transmission spectrum, there are already chemical constraints, and it's been shown that its chemical abundances are between 1 and 100 times solar. So that's the range we're going to consider here. And for the internal temperature, obviously that's very difficult to measure observationally, as I showed before, but it is possible to estimate it with planetary evolution models, which is what is usually done. So here we took an example from Valencia et al. 2013, and they calculated for GJ1214b, which has a roughly similar mass to K218b, that across a wide range of ages and different atmospheric compositions, we would expect the internal temperature to be between about 25 and 50 Kelvin. So we're going to use that as our exploration range in this part of the work. And then more recently, in a paper that was led by my supervisor, Madhu, we investigated different internal structures and compositions that are possible for K218b. And we found that the pressure at which a surface could exist between a water layer and the hydrogen-helium atmosphere could actually occur at fairly low pressures. So even as low as a few bar or tens of bar in some cases. It is a degenerate problem, so it's possible that the surface would actually be much deeper, but there are solutions that exist with low pressure and low temperature solutions. So for this particular case study, and just to sort of explore these conditions for this type of planet, we wanted to ask the question, if a surface does exist with a water layer at a pressure of less than 1,000 bar, what would be the potential surface conditions of that water surface? Could we get a liquid ocean? Could we get a habitable ocean? Is it possible? And what kind of atmospheric conditions would we need for that? So starting off, we're exploring these different metallicities, as I said, between 1 times solar and 100 times solar. And then for each of those metallicities, which are different colors, we're also exploring a model with an internal temperature of 25 Kelvin, that's the cooler ones, and a model with an internal temperature of 50 Kelvin, the hotter ones. And initially, we're just looking at a model with no hazes. We include water ice clouds wherever they're necessary thermodynamically, but we're not adding any hazes. Here, this yellow region is the same as before. It's that region of pressure less than 1,000 bar, temperature less than 400 Kelvin, that in theory, if a surface occurred in this range, the liquid water could potentially be habitable. So we find that for the lower metallicity cases, these are going through this sort of yellow region. And that means that if the water to atmosphere boundary happened somewhere in the range, shallower than 1,000 or so bar and deeper than about 1 bar, it would be possible for the surface of that water layer to be both liquid and potentially habitable. But if you go to the higher metallicity of 100 times solar, that's not really possible, only in a tiny range. And actually the greenhouse warming makes it much too hot, and you would actually have a transition into water vapor or supercritical water instead. But if we now consider models that also have haze, then these higher metallicity models actually are cooled by the haze and do enter this phase where it's possible to have a liquid surface and potentially habitable liquid surface. So that's just to show that actually considering clouds and hazes and that optical scattering is really important, because it has a significant effect on the temperature conditions deeper down in the atmosphere, and it does make a big difference. So that was for our case study of K218b, but you might be asking, well, that's like very nicely in this habitable zone. What if you have something that's a little bit hotter? So we also considered a case that looks exactly like K218b, but about 100 Kelvin hotter than that, just to see what those conditions would look like. So in the case with no haze at all, we can see that all of these models are actually far too hot to have the liquid water surface. So any transition to this water layer would be in the vapor phase or the supercritical phase. But again, if we add hazes, it cools down all the temperature profiles. And it is possible, if you add enough haze, to pass through this liquid phase and even the potentially habitable liquid phase. So again, the haze is playing an important role. And so thinking about in the future observations of atmospheres, it'll be useful to be able to constrain whether there is haze or not in these atmospheres, and current observations are hinting that there is. So that's useful and interesting to think about the conditions that might create deeper down. So so far I've been doing this with abundances, the different metallicities of 1 to 100 times solar based on the transmission spectrum measured for K218b. But you might be thinking, if we actually had a liquid ocean beneath the atmosphere, that ocean might be evaporating and it might have you might expect a higher relative humidity above that ocean. So we decided to also consider this other extreme, where above the ocean, we have 100% relative humidity in the atmosphere. We consider this for a couple of different ocean pressures. The first one is with an ocean at 1 bar, and we find that actually it doesn't take too much haze for these solutions, these temperature profiles, to be consistent with the liquid ocean. So even though we're getting a lot of extra greenhouse warming from this high abundance of water, because we're saturating the water abundance, it's still allowing at 1 bar these cool enough temperatures for liquid, and even a liquid ocean cooler than 400 Kelvin, so potentially habitable. And it takes a fairly modest amount of haze. And then if we consider an ocean deeper down at 100 bar, by that point, there is a bit more greenhouse warming, and also the internal temperature becomes more important because we're deeper down. So these dashed lines are showing models for a higher internal temperature, and so they are hotter and still allow for a liquid solution, but a very hot one. But for the lower internal temperatures and with a bit more haze, we can actually still get fairly cool models, even with an ocean surface at 100 bar. So even in this extreme limit of 100% relative humidity, we can still get solutions that are consistent with the presence of that ocean to begin with. So that's an exploration of the different conditions within the planet, but what could we expect to actually see, for example, with James Webb? So for some of the models that I showed earlier, I've also calculated the spectra that we would expect to see with MIRI photometry, assuming some optimistic error bars of about 10 ppm. And so certainly because these objects are so cool, on the order of 300 Kelvin, it's difficult to make compositional constraints. But what we can do is to measure the temperature in the photosphere. And that's quite useful because it gives us one data point, at least, of the temperature conditions within that atmosphere. And we can use that as a limit of what the temperature conditions might be deeper down in the atmosphere. So for example, if we measure a brightness temperature of 300 Kelvin, then we could imagine that if this is an atmosphere with high optical scattering, it might be very isothermal. And so even at higher pressures, if there's a surface deeper down, that surface could be at temperatures not much above 300 Kelvin because it's so isothermal. But on the other hand, you could measure 300 Kelvin in the photosphere and there could be loads of greenhouse warming, like this purple case, and actually at a surface deeper down, it would be very hot and too hot for liquid water. But it provides that limit such that if we observed a 400 Kelvin photosphere, chances are that it would be very difficult to get any habitable conditions deeper down, because even if you had a super isothermal temperature profile, you would still be hitting 400 Kelvin at your surface. So it's a way of providing some kind of initial limit on what might be happening deeper in the photosphere. And this is for quite cool objects. So for warmer mini-Neptunes, of course, we could do a lot more and get compositional constraints. For example, this is up here again with MIRI photometry, and this is a nice CO2 feature. which we could see with that. And we can also make place good constraints on the temperature profiles as well. So the warmer mini-Neptunes can provide us these insights into the chemistry for those objects, and then the cooler ones, it'll be exciting to see what we can learn about their temperature profiles and what that could mean for the conditions below. So just to summarize, I think I've just managed to stick to time. So the atmospheric properties in the atmosphere really impact both the energy transport, for example, where the radiative convective boundary is, and it really affects the temperature conditions deeper in the atmosphere. Clouds and hazes are really important in determining those temperature conditions. So even though they're a bit tricky to model, I think it's very important going forwards that we do include them. And mini-Neptunes such as K218b, which could have surfaces at relatively low pressures, they could have conditions that are conducive for liquid water surfaces, depending on their atmospheric conditions and their internal structures. And finally, James Webb will place really interesting constraints on both the chemistry of the warmer mini-Neptunes and also the thermal properties of a whole range of different mini-Neptunes. So lots to look forward to. Yeah, thanks very much, and I'd be happy to take any questions.
Thanks, Anjali. So that was a really tons of interesting stuff. Yeah, give her a hand. And what we'll do now is, if you have a question, please raise your hand, or if you want, you can put it into the chat, and then I'll go ahead and read them off if you prefer not to ask them. Otherwise, you can ask them directly. So I'll wait a minute for that. I have some questions, but I will not hog the mic on this. All right, Vlad, I think you have a question. Go ahead if you want to go ahead and ask.
Yes. Yes, hello. Thanks for interesting talk. Yeah, I have a couple of questions regarding those L and T-Dwarfs. So, as far as I know, the radio observations of those objects show pretty strong magnetic field from 3 to 4 kilogauss. So if we calculate the photospheric pressure exerted by the magnetic field, it will be pretty strong. It's going to 10 to the 5 dienes or something, which is comparable to the thermal pressure, the photospheric pressure, which suggests that this, when you write this equation for the, equilibrium, for hydrostatic equilibrium, so it's not just the thermal pressure, but also the magnetic pressure should be taken into account. So that's the first question. Have you considered that? And the second is that when you go to in the atmosphere, to at heights at the level of like millibars or so, the non-LTE effects become dominant compared to LTE. Have you taken into account non-LTE? Thank you.
So for your first question, we don't include the magnetic effects. Could you remind me the pressures that you said that was important at?
10 to the 5, 10 to the power of 5. Yeah,
okay.
Which is, I think it's the pressure. At least my estimates during your talk was kind of like 5 10 to the power of 4. If you assume the density 10 to the 17 centimeter minus cube, and the temperature about 3000. So that will give you about 5 10 to the 4, and the pressures from magnetic field 1.4 10 to the 5 dienes. So basically, it's going to be a factor of 3 greater, or at least comparable. So that just a suggestion to.
At the deeper pressures, then.
Pardon?
So at pressures of 10 to the 4 bar, did you say?
Oh no! I'm talking about the photospheric pressure.
Oh, in the photosphere. Okay, yeah. So yeah, we haven't included the magnetic effects, but that's very interesting to hear. That would be interesting to include that and see how that affects the retrievals. I think that's really cool. For the second question, was the non-LTE.
Right.
And so that, I expect, affects the much lower pressures, and in these Brandls, we're really probing much deeper pressures. So I think the non-LTE effects shouldn't affect. So I see how in a self-consistent model that could maybe affect the heating and cooling rates, or from an evolutionary cooling point of view. But here, because we're doing a parametric retrieval, and the data is driving, is basically telling us what the temperature profile is just in the photosphere. We shouldn't be affected by the non-LTE effects at the lower pressures that we're not actually sensitive to with this data.
Thank you.
Other questions? Okay. Looks like Avi, you're up next.
Yeah, thanks, Anjali. Great talk. I was wondering about, I know this wasn't maybe your work specifically, but this question of these internal structure models about the actual position of the constraints on the surface position. How much is that dominated by the uncertainties in the data for mass and radius for the planet versus the question of equation of state or other factors related to modeling that? And I guess, what do you think our chances of better constraining that in the future might be?
So even with perfect mass and radius data, there's just an intrinsic degeneracy that's occurring in this case because the density is sort of similar to that of a 100% water planet. We could have, very dense rocky core and a huge hydrogen atmosphere, or something that's like super water rich and doesn't have as much of a core and atmosphere. So there is that intrinsic degeneracy there. And yeah, if you add the error bars and mass and radius, that adds more solutions that are possible. But even with no error bars, there's that degeneracy. So yeah, there's been lots of interesting work on how to kind of break that degeneracy to a certain extent, like looking at the stellar abundances of different species and looking at multi-planet systems. I know Caroline Dawn has worked on that quite a bit. So that's one way to try and investigate that a little bit more. It is tricky. So ultimately, I think it has to be an approach from multiple sides, both looking at the system in general and what kind of chemistry we would expect from that and the stellar abundances, but also hopefully maybe the atmosphere could start to give us some information about any surface that's present. For example, if you have an ocean and that's sort of catalyzing any chemical reactions, or you can see a certain abundance of water vapor and things like that, that might be able to give us some clues as to what's going on in the interior. But it's definitely going to be a multifaceted approach, I think, because there's such an intrinsic degeneracy in there.
Great. Additional questions? Otherwise, I will go ahead and ask mine. I'll wait another 10 seconds for that. All right, it's kind of related to Avi. So in terms of the uncertainty on the gravity that you see here, that's obviously going to be related to that mass and radius too. But I imagine that also determines kind of photosphere location by determining where you have condensation and things like that. Do you find that that is another kind of degeneracy related to kind of abundances, things like that? How would you think about like kind of breaking that?
So for the mini-Neptunes, because we're looking at sort of compared to the brown dwarfs, we're looking sort of at a somewhat, well, it depends on the case, but because of the size of the atmosphere, we don't consider the uncertainty in the gravity so much, because I don't think that would change our results very much. It's true that there is that degeneracy existing for brown dwarfs because we don't know the mass and radius at all. So then you can get a very large distance, but for the uncertainties for the Mini-Neptune, that's small enough that it won't really impact. It would truncate that on that sort of 2D posterior correlation, it would really truncate that to a small circle. So then it doesn't have so much degeneracy because we know it well enough. But then for the brown dwarfs, it is still an issue just because we don't necessarily know the mass and radius at all. I don't know if that answers your question.
Oh, that totally makes sense. Yeah, it makes sense for the Neptunes. You're not really getting much of an effect.
Yeah.
Let's see. Any other questions? Otherwise, I'll ask one more. All right. So you kind of allude a little bit to kind of clouds and cloud position, composition. So how different is that in terms of, like, I know that's a monster in terms of modeling and in terms of kind of choosing a lot of everything from position to morphology to all that other stuff. Is that something that you would explore in the future for Neptunes as well? Yeah,
definitely. So the clouds and hazes are both tricky. Maybe hazes are even more difficult because there's so much uncertainty on where they come from. And then clouds, at least we know where we expect things to condense. So then it's a case of particle sizes and sort of nucleation and things like that. I think on the whole, as with many things, a sort of hierarchical approach is useful. So, having lots of people who have very nice macrophysical models and looking at clouds in detail. And then there's also an approach of having a simpler parameterization, but then exploring different ranges of those different parameters that you're using to see how sensitive we actually are to different parameters. So I think both of those approaches will be needed in the future. And actually seeing how clouds and hazes affect solar system objects, I think is quite useful because it can give us like a nice data point of, okay, well, how did this actually happen in this big parameter space of all the different cases? This is something that really happened. Maybe we should consider that happening on exoplanets too. So I think, yeah, multidisciplinary approach will be needed. But as I said, I think we need to be doing that because it can have such an important effect on both the atmosphere and the surface underneath it. So it's tricky, but we should strive to do it anyway.
I think we'll all endorse the exoplanetology study of like comparative cloud study. Any other questions? If not, you can also email me, or if you have a question that comes to you later, you can email me and I can pass on Anjali's email to you so you can ask her directly. We'll also be posting this video. Actually, it looks like Avi has another question. Go for it, Avi.
Yeah, I just wanted to ask a little bit about that question of the surfaces that you might, or surface atmosphere interactions you might expect at high pressures. How much do we know about how, anything about water dynamics or sort of the outgassing of material from, do we know anything about how that might work? Because I imagine at the base, if you have a very high surface close to low, or a low pressure surface, that would make a significant difference. But I don't know.
Yeah, so one thing that has been looked at a little bit by Subaran and Minitzer, I think, is the mixing of the water and hydrogen phases. So the possibility of, instead of having a surface, having more of a gradient. And so that's one thing that isn't really constrained, I think. There are theories about it, so it'd be interesting to see under what conditions you actually get a clean surface. And then in terms of the actual, if you do have an ocean, what would happen? There are, ideas of, models that have been done of the chemistry that can be enabled by an ocean. I think a lot of these, though, also include land. So the idea of having like a full ocean planet is also a slightly different kettle of fish, I guess, from that point of view. So yeah, I think a lot more to consider in the future. And yeah, there are simple things like whether you can see a water abundance that's consistent with some kind of high relative humidity from the ocean, but then maybe depending on the chemistry of the atmosphere, I'm not sure how easy it would be to say, okay, this reaction needs to be catalyzed by an ocean or something like that, but something hopefully the chemists can tell us.
Great, thanks.